Hello everyone, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois. And this video today, excuse me, is going to take a look at bubble sort using the C++ programming language. So the bubble sort is one of many, many different ways we can take a collection of data and sort its contents. And so like many, many, many different ways here. So what are we trying to do in general? We all know how to sort. Like some of us have done sorting more than others, depending on your jobs and things you've done as children. We used to actually have these things called CDs and DVDs growing up, where we would have a whole collection of them, and we would actually, we had enough of them where we would alphabetize them and put them in some order. People these days don't have that. The computer organizes your electronic collection for you. So like I said, I've basically used all of these out in the real world before I ever realized that there were different algorithms in a way to solve these kind of things. So we're going to, you can sort alphabetical or numerically, or there's other ways you can sort too. You can kind of customize your sort however you see fit. But they say, like in our way, we're going to keep things to what is called bubble sort, as you say. That's the name of this lecture today. It is basically the second worst algorithm there is when it comes to sorting data. And the reason is because there's a lot of testing and a lot of swapping going on to get data from point A to point B and to make sure everything ends up in the correct places. And so the worst one is just to randomly swap two values and then ask the question, is it sorted yet? And that one you might never finish depending on the size of the array, because that one's a factorial when it comes to what we call big O notation. And so yeah, n squared is a big deal when this is what this algorithm is, bubble sort. But n factorial, yeah, that's a little worse than n squared. So coming back, what is our plan? Our plan of action is to progress through a collection of data, an array of data, basically two elements at a time, start with the first and second elements, check them out, and see if I need to swap them based on the criteria of trying to put the smaller numbers to the left and the larger numbers to the right. And I just go and I just check and go, do I need to swap? And I do if I do, and then I move over one and I try again. And I move over one and I try again. Move over one and I try again. And I go through the whole list that way. And basically what will happen is if I can go through one whole pass, because I'll make a pass, and then I'll go, hey, did I swap anything in the case, did I swap anything as I was going along? And if the answer is yes, then I need to make another pass. And so I have to go through the entire list and make all of these comparisons, and I know I'm done when I go through the entire list and the entire collection and I don't make a single swap as I go. Then I know everything has bubbled and is now into the in the place it's supposed to be. And so that's all there is really to it, is say that the algorithm is a little different, it's a little more efficient than it was back when I was going through things. Researchers have found a better way to take bubble sort and make it a little better. It's still a terrible, terrible sort compared to a lot of the cooler ones, like quick sort and merge sort and heap sort and those kind of things. Those are much more challenging algorithms to understand. But this one is, conceptually very simple. And that's generally how things work in computer science. Not always, but the easier conceptual ideas are worse algorithms, and the ones that just kind of melt your brain trying to figure out how they actually work, those are the ones that work as efficiently as we know how, and maybe as efficiently as possible given the circumstances. And so the benefit of this is, as I was saying, it's easy to understand, but the disadvantage of this thing that we're going to do here is that it's completely slow. We're talking slow compared to other ways of doing things. So I have a collection of data here, so let's just do one example before we write the code for something like this. And I say, okay, I have this collection of data and I want to do stuff to it to make everything work out and make everything sorted so it goes 1, 2, 3, 4, 5, 6, 7. So as I was saying, I'll make one pass through the data. So here we go, here's a pass through, and I just check these two, I go, do I need to swap them? And the answer right now is yes, 2, 3. And then I move over here and I go, do I need to swap those? And I go, no. And okay, how about these? And I go, yep. And then I go, well, how about this? And I go, yep. And then I go, how about this? And I go, yep. And then I go, how about this? And I go, yep. And so what do you notice? Things that you've noticed is things are getting a little better. Maybe not. I mean, it depends on your perspective. But in one regard here, things are starting to move a little bit, right? The 2 has moved over, the 3's moved back a little, but the 6 is over, the 1 is over, the 4 and the 5. And the one thing that is certain, the largest number in our collection is, it's called bubble sort, but it also could be kind of called like, just fall rock bottom, fall as fast as you can to the bottom sort. The largest number has just flown. Everything else can only move up, you can only move up one, but you can fall all the way to the bottom. And so the 7 has done exactly that. The 7 is technically sorted because it's done. There's nothing left to do. And so we've made passes, so we have to just do the whole algorithm another time. So I go, okay, 2 to 3. Do I need to sort? Nope. 3 to 6. Do I need to sort? Yeah. No, I don't. Do I need to do 6 to 1? Yep, I got to sort those out. And do I need to take 6 to 4? I go, yep, you can see where this is going. So 4 will go here, 6 will go there. Same this here. Yep, this needs to go. And then if you want to, you don't even technically need to do the last one, but you can if you want, because 6 will now, yes, these are correct in place. And so now these two values are correct in place, and everything else may or may not be. And the reason why we're not sure is because we made a swap. Maybe we could look at it if we were humans, but the computer can't make that distinction. The computer goes, well, we've made swaps as we went along in this pass, so right now I have to make another pass. And it's just a coincidence that the 5 made it here into this spot. It's not like nothing, it just moved up 1 to accommodate for the way it was placed. So let's go again. And we say, okay, 2 to 3, okay, yep, that's fine. 3 to 1, yeah, we need to swap those out. 3 to 4, nope. 4 to 5, nope. 5 to 6, nope. 6 to 7, nope. So we're getting even better now, right? And so we made a pass, but now we're getting closer. You can see that things are getting very close to where we need to go. So one more pass, and you go, okay, yep, I do need to swap this. And I don't need to. And the thing is, it is sorted, but we don't know that yet. The computer, again, only knows that it made a swap while it was doing whatever it was doing. It doesn't know that that one swap could have been something we still need to propagate through the system. And so we need to make one more pass through now and go, nope, and then we're done. And now it is now we can guarantee that our collection of data is sorted. And so the whole point of this is if I didn't do the check to see how, if I just went ahead and said, if there's 7 elements, I made 7 passes, then I can guarantee, because what if the 1 was over here and you go 1 pass, 2 pass, 3 pass, 4 pass, 5 pass, 6 passes. Maybe it needs n-1 passes, but it needs a lot of passes. And this only made 5 passes. This only went pass 1, pass 2, pass 3, pass 4, pass 5. And so the reason for the efficiency gain in this algorithm is, what if I started with this and said sort? And the old algorithm was blind to the fact that this thing might have already been sorted, or it might have been sorted at any pass along the way, and it would just blindly check every element against every other element, and it would take the same amount of time no matter what, even whether it's sorted or not, to do the job. But now with this improved algorithm, we can just go ahead and in one pass we just go sorted, and we're done because we didn't make any swaps along the way. So again, it's an improvement. It's still not a great way going about doing things, especially if your lists aren't sorted. So if the only time you get that performance gain is basically in certain situations, and I don't know enough about it to know exactly what kind of situations other than closely sorted, but not quite, but all the numbers are close to where they need to go. Anyway, so how would I write this code in C++ at the very least? I'll use an array, and we'll go ahead and write this out. It's hopefully a pretty short lecture. So I'm going to start out with an array of data. I'll do the same thing I did here. I'll just call it array. I'll just int array, and I'll do it the best practices here instead of hacking it out. 7 elements, call it array, and I will set this thing equal to what we had before, 3, 2, 7, 6, 1, 4, 5. Okay, there now. And so before we get going, I would like to set up a function called print that takes in an integer array, and then its size, and prints all the elements out, just so we can see things as we go, and then we can see if I made a tiny mistake as we went, and I made just as I was doing, I very tediously forgot to do a swap or something like that. So we'll see. Hopefully my results will end up the same as before. So for int I equals 0, I is less than size, plus I, C out array at the I location, add a space, and then here do an endline. Okay, so then now just to prove I got everything working, I can send the array and size over, and let's see what this thing prints out as. And there we go. 3, 2, 7, 6, 1, 4, 5. Okay, fair enough. And so now what I would like to do is call a function called bubble sort, pass along the array and the size, and I would love for this thing to come back sorted, bubble sorty. And so the signature is the same, because remember, I'm passing, even though you don't see an ampersand and you think you're passing by value, arrays get passed by reference / pointer no matter what. So by changing the data and swapping stuff around inside of the inside of the bubble sort function, we'll be changing the real data. So when I get down here and after it's all said and done, we'll print everything out and it will be sorted once it's all said and done. So for right now, yes, we have the begin case and the end case, and we go, oh, we got some work to do. We definitely have some work to do. So let's make one pass. Let's just try one pass through, and then we'll add the secondary loop, and then it should be pretty good. Again, simple conceptual thing going on here. So there's 7 elements, and I want to check. Let me put the element numbers out here, just so we understand what we're doing. So I want to check 0 versus 1, 1 versus 2, 2 versus 3, 3 versus 4, 4 versus 5, and 5 versus 6, and swap as I need to go. So there's definitely some kind of loop structure here. And so just to say, the array size is 7, right? There's 7 elements, and I need to check, I need to check, I'll just color these. I need this versus this. I'm just putting them in different rows just to make my point here of how many different things we need to do. So there's going to be 1, 2, 3, 4, 5, 6 checks. There's going to be n-1 comparisons. If there's n elements, there's going to be n-1 comparisons to make. Which means this for loop starts out okay, but it's not exactly what I'm intending to do, because if I just go up to, if I just say, okay, let's use 0, and let's use 1, and let's use 2 for I value, because I'm going to do I and then I plus 1. But if I go over to less than size, that'll be 6, and then if I use 6 plus 1, I'll be over an element 7, so I can't use element 7 because that's outside of the array. And I see this during exam time when I give this out for exams, depending on the class you're taking. And it's frustrating because you could tell all they're missing is just this one little thing in their program of work, and I can't tell them because it's an exam, and it's just frustrating. And that's because, again, I need to go down to less than size minus 1. I need to go down to here, less than 6 instead of less than 7. Okay, so, but what am I doing? If array at I is greater than array at I plus 1, and there's a function in the standard library called swap, so you don't have to do the code yourself, but just to show you how the code works, I could say give me a temporary variable and set it equal to array at the I location. Take array at the I location and set it equal to the array at I plus 1 location. And then take array at the I plus 1 location and set it equal to temp. And wouldn't you rather just call swap if it already knows how to do it, like the function is already as efficient as it can get? And so let's see what happens. We're just going element for element. We're just testing 2 at a time, and we're seeing if we need to swap the 2 up. And so what do we get? Okay. Oops, let me bring this back. Okay, so this is the row it should be, right? This is the I got a little confused there. This is the first row, which is what we agree with, and this is after our first pass. 2, 3, 6, 1, 4, 5, 7. We agree. Cool. And so, and I say, if I really want just to kind of, this doesn't automate it by any means, but if I just repeat this over and over and over again, eventually you will see that this thing will come out right. But again, now that the final test of this is, how do we know when to end the number of bubble sorts? Because you're never going to want to hard code this. And so we need to know if, like during the course of going through this algorithm, did I make any swaps whatsoever? And so in this case, I could say, yep, there were no swaps made, but when I get to here, I did make a swap. True, fair enough, right? And so what we can do here is say, as long as, that's the fun of this, right? As long as I make a whole pass through, and when I get done, if the number of swaps made was 0, it doesn't matter if it's 1 or 2 or 100 swaps made, as long as it's 0 versus non-zero. And that's why it's, swap made false versus true here. And so if I put another loop around this and say, okay, if I get to this point here, and this is like a do while, because we have to do this at least one time, and I can say while swap made is equal to true. As long as the swap was made, I want to keep going. And so this breaks down on me, because when I hit this closing curly brace, swap made here goes out of scope. So I can bring it up to here and put it here so I have it in both places. And now, let me move a print statement. Let's just move this all together out and put this into here. Oops. So I'll print the bubble sort at the start. I'll print the bubble sort after every single completion of every progression through. Let me replace the size here. Okay, and then when it's done, it'll be, if this is correct, it'll be printed, it'll be sorted. So every pass it takes should be printed. If I did this right, crossing my fingers now, and there you go. It made exactly as many passes as it needed to, just like we were discussing. It has 6 rows, just like we have. It duplicates twice because, as we discussed earlier, to get to this point, we had to make a swap during the pass. And because we made a pass with a swap, we had to go one more time through, to make the understanding that it is completely sorted now. And you can see, we totally agree on this. The 7, the 6, the 5, like it's every pass slams the next largest number down as far as it'll go, and it bubbles up the numbers it needs to at one time and one time only. So it slams down and bubbles up. And then we have it. This is the whole algorithm. And if I said, coming back to this, I could say swap array I, comma, array I plus 1. That is all there is to it. It does, and that's done. That's automatic for us. And like, if you want to get technical, you could remove some of these curly braces. But again, I do highly recommend you don't do that. So we can get rid of the print statements now. Like we said, we're pretty much happy with what we've got. So now we say you should never do the printing. The job of the bubble sort function is to bubble sort. It's not to print anything out. That is up to me on my end if I want to print whatever it is I want to print. We bring this back to size here, literally and figuratively. And now, coming back one more time, here we go. And it prints the prior and it prints the post, and it just works. That's our bubble sort. Not a lot of code. But again, it's not conceptually that difficult either, but it's horrendously slow because it takes, the way it progresses through, it's doing n check or n minus 1. It's n minus 1 passes at the maximum, right? If the thing was completely resorted, and it's taking n minus, and it could do n minus 1 swaps in each pass. So that's n squared minus 2n plus 1 when it comes to the number of comparisons and the number of swaps it could do. And when we talk about algorithms, the n squared is the term that matters to us. And so this is an n squared algorithm, and it's a horrendous one at that. We can use selection sort and insertion sort to do a better job, but they're still n squared algorithms, but they're slightly better because they do less swaps and less comparisons to get the job done. Maybe, do they do less comparisons? At least they do less swaps for sure. Because this one is the worst of both worlds because it does a ton of comparisons and a ton of swaps. Alright, so that covers bubble sort, the second worst algorithm of them all when it comes to sorting, but a very simple algorithm to comprehend. So As always, if you have any questions or comments, swardb@cod.edu is a great way to get a hold of me. Another great way to get a hold of me is to comment here on YouTube. Like and subscribe. So anyway, I hope this was enlightening for you, and hope you watch my future videos and maybe my past ones too. Have a nice day, everyone.